Going to do another example now. We're going to look at the polynomial ring over Q in the indeterminate x, and we're going to mod out by the principal ideal generated by x minus 5. Now, before we do this, let me give you one more perspective on the previous example that I didn't do, but I feel like it's good to go back and look at. So when you mod out by an ideal, you declare things in that ideal are 0. So modding out by x over here is saying, hey, I want x's to be 0. So if I take a random polynomial and I declare all of the instances of x are now 0, what effectively happens? Well, we are going to declare all of these x's are 0. So what should happen? Well, it should be I pick out the constant term. And so that's another way of thinking about this problem. When you mod out by an ideal, the things in the ideal become 0. And so if you look at a general element and you just look at where the things in the ideal are, and you write a 0, it gives you more intuition for what you should get. So with that in mind, what this is saying with this problem is saying, hey, I want x minus 5 to be 0. Or similarly, what I want to do is I want to plug in I want x to be equal to 5. So if we take a random polynomial, which is built with like rational coefficients, and we declare all of a sudden that x is 5, what are we going to get? Well, we'd better still get some rational numbers, right? So in other words, if we want some intuition for what this guy should be, perhaps what we should do is we should consider some sort of function that plugs in x equals 5. So let's try that out. So let's consider the evaluation at 5 function. And where should it go? Well, it could go to a lot of places. It could go to R, it could go to C, it could go to Q, it could go to other abstract things that contain these guys. But if we want to identify this object, the quotient ring up here, we don't want to go to larger things. We want to go to sort of the smallest thing that makes sense. And I claim the smallest thing that makes sense to do is to go to Q. So we're going to consider the evaluation at 5 mapping from Q adjoin X to Q. And just a reminder, evaluation at 5 of some polynomial is plug in 5. Or if you were to write your polynomial out with rational coefficients, so the a's are rational, it's going to be the I will plug 5 into you function. So again, our coefficients are rational numbers. And this quantity is again a rational number because the rationals are closed under arithmetic because they are a ring. Well, they're a field, they're even better. Or they have more structure at least. So it makes sense as a function. Okay, we already know that evaluation at 5 is a homomorphism. And in fact, it's also onto, so it's an epimorphism. Why is it onto? Well, you evaluate constant polynomials and you'll get anything that you want. So evaluation at 5 is a homomorphism, and onto, so it is an epimorphism. Let's argue that the kernel of evaluation at 5 is precisely the ideal generated by x minus 5. And this is a cool trick that I showed you how to do in class, but I'm going to show you again because it's good to know. So let's see. So let's do one of the containments. So let's do the backwards containment. So suppose that you're a multiple of 5. So you're x minus 5 times some p of x, and that's in the ideal generated by x minus 5. Then when you apply evaluation at 5 to that multiple of x minus 5, you're going to get 5 minus 5 times p of 5. And it doesn't really matter what p of 5 is because there's a 0 out front. So what this tells you then is that every element in the ideal generated by x minus 5 is in the kernel. So this guy is a subset of the kernel. Suppose now, for the reverse containment, suppose that you have some f of x in the kernel of evaluation at 5, and we're going to use the division algorithm to find, well, Q and R such that we have a field here, right? So Q is a field, so we can use the division algorithm, such that F is x minus 5 times some quotient plus R, where the degree of R is less than the degree of x minus 5, but that's a 1. So the degree of R is less than 1. So if R is 0, it's negative infinity, and if R is a non-zero constant, it's 0, and those are the only options. So this tells us then that R is a constant. 0 is also a constant, so in either case it's a constant. Let's call that constant just little r. So in particular, f is going to look like x minus 5 q of x, and then for degree reasons, a constant. So this guy is just an honest, hard-working, rational number. All right, so none of this actually used the fact that f was in the kernel. I just wanted to divide that ahead of time. Now let's use the fact that f is in the kernel. So when we evaluate f at 5, we get 0 by evaluating, or we can plug in what f is equal to and we can evaluate that instead. All right, so evaluation at 5 is a homomorphism, and so we can just plug 5 into this expression. We don't have to worry about pluses and whatnot. So 5 minus 5, q of 5. When you plug 5 into a constant, you just get that constant. Now 5 minus 5 is 0, so like earlier, this part goes away entirely, and we're left with r. R is equal to 0. So the remainder is 0. So f is x minus 5 times q of x plus 0. F is just is a multiple of x minus 5, so it's in the ideal generated by x minus 5. So just a quick reminder, we took something in the kernel, we divided it by so what we did is we took like the best approximation to being a multiple of x minus 5, and there's this error remainder term, and we showed that error was 0, so actually f was a multiple of x minus 5. Okay, so this means that the kernel of evaluation at 5 is contained in, and so they actually have to be equal, because this was the other side of the double containment argument. All right, and so the kernel is equal to that. So let's go back up real quick. Evaluation at 5 is a homomorphism, which is an epimorphism. The kernel of that evaluation mapping is exactly the ideal we cared about. And so we can conclude then, by the Noether isomorphism theorem, we can identify this this guy, and we find that q adjoint x mod x minus 5 is exactly q, the codomain here, which happens to be the range. Great. So let me just say here, there's nothing special about 5. And there's nothing special about, 0 in the previous video. So if you pick your favorite rational number, and you mod out by the ideal generated by x minus a, you get exactly q. How can you prove this? Well, you look at all of this work that we just did, and you replace all the 5s with an a, and absolutely nothing changes. Okay? So it's exactly the same proof. And this is also the same for the previous example with z adjoint x.